The receiver part in here that I highlighted in red is a system that tries basically to estimate the middle of a data bit or a parity bit and tries to sample it and push it in from the RX. That's its main purpose. And the way we're going to implement it is using a finite state machine. Really, that finite state machine takes the following two inputs. It takes actually the outside world receiver or RX, and it takes that bit, the ticks from the baud rate generator. And once it's done, it just assembles that data and just basically pushes it out and tells me that it's done. That's how it does it. That's how the receiver is doing it. Of course, it's just a finite state machine. So let me show you how it's constructed. So in here, I'm showing you the ASM chart, or the algorithmic state machine chart, as opposed to the state diagram. And really, the reason why I'm showing you this is actually because I need a little bit more modification, or I need to show you something else. So technically, this is not an ASM. This is what we call an ASMD. Okay, so there's the word D in here, because what I'll be showing you is some data manipulation as well, because usually finite state machines manipulate data and how data is moved. So what I'm really showing you in here is what we call an ASMD, which is an algorithmic state machine with data. Okay. Anyway, so let me explain how the whole system works, and then you'll figure out what do I mean by data in here. So what this diagram shows me is the following. So I have these dotted boxes in here, and these dotted boxes usually are just highlighting the states of this finite state machine. So the state usually is associated with this here state box, and after above the state box, I usually have the name. So what this tells me is I have an idle state, I have a start state, and I have a data state in here, and I have stop state in here. So I have four distinct state for this finite state machine, and as the names of the states imply, this is usually when I'm in idle state. This is when I have detected the start bit, or when I'm trying basically to do the middle of the start bit, and this is here when I'm receiving the data, and this is when I'm issuing the stop. So let me walk you through this particular diagram just to show it one at a time. So I'm just going to zoom in a little bit in here so we get to see it a little bit better. So in an idle state, what you see is the following. I will ask, is the RX, which is basically the receiving, 0? Remember, in an idle state, the line is usually kept high, and take a look at the UART protocol description, but usually the line is kept high. So I'm looking for RX to be 0. Whenever it's 0, well, if it's not 0, you're going to keep staying in idle. Once it hits 0, you'll actually do the following. This is where the D stands for, because I'm moving data. So you're going to see in here is the following. I have something called S, and that S is just a register, and that register I'm putting 0 in it. What does that S register stands for? Well, it's some sort of, actually it's a counter more than a register, and it actually counts the number of ticks. So let me just say it counts the number of S tick. That's its main purpose. All right, so what did I put in it? Well, I put the number 0 in it. Okay, why did I put the number 0 in it? Because I want to know how many ticks happens. And remember, in a start bit, what I'm trying to do is I'm trying to detect that middle point, so that from now on, like if I count for like 16 ticks, I'll be in the middle of each one of the data points. Of course, what this tells me is the minute you get Rx equals 0, you're going to get S will be 0. Okay, the value of S will be 0, and then you're going to move to the next state. And the next state is the start state, which detects, or which just tries to figure out the middle of the start bit. So how does it detect the middle of the start bit? It actually goes in here, and it asks, is S tick equals 1? Remember, the S tick is generated by the baud rate generator over there. That's the timer that is ticking. And as long as it's false, it just stays in it. Once it's true, this is what the T stands for in here, we're going to go and ask, is S equal 7? Remember, this is keeping track of how many S ticks did I receive. And the 7 is actually the middle of the 16, about middle. Okay, and once if it didn't reach it and the answer is false, I'm going to add 1 to it. Remember, that S is a counter technically. And we're going to go again, and we're going to keep doing it till we get the S equals 7. Once we get 7, we're going to say, well, the answer is true. Now I'm going to reset that S again, and I'll create something else which is called N equals 0. So I have another counter or register, and really this actually tells me the number of bits that I shifted in. That's what N stands for, or that particular register in here. All right, so of course, like if that happens, that means I'm in the middle of the start bit in here. Remember, because S equals 7, I'm in the middle of the start bit. And what I did is I resetted that start bit, the S tick counter, and I reset it N because I didn't receive anything. And the next state will be, well, let's receive some data. Okay, so we received some data in here. So this is the data state. And in the data state, I'm also asking for the S tick because remember, I'm trying to detect the middle of that S or that particular data bit or something that I received. And then at some point in here, you basically stay in it, and then you're going to ask, instead of s equals 7, I'm asking s equals 15, because now I'm going from 0 all the way to 15, which is 16 exact bits. And if I'm not at 15, I'll just add 1 to s, I'll just add 1 to s, I'll just add 1 to s. Once I reach that 15 number, I'll have the following. First, I'm going to zero out that s tick, because I need, for the next bit, I'm going to restart that count. And now I have another register. And really, that's the actually shift in register that I actually care about. Okay, and that's what I'm trying to do in here. It actually will have the valid bits, or actually the shifted bits. Let me just call it shifted bits in here. Okay, this will have the shifted bits. All right. So what this indicates in here is I will take whatever Rx I have and I'll OR it with a shifted version of that B. That's what this means. That means I'm going to shift it to the right, and then I'm going to OR it with an Rx just to keep everything in. Anyway, bottom line is I'm shifting, like if I have a 1 and I already had a 1, I'm just shifting another 1 inside. That's what this means. And then after I'm done in here, I'm going to ask, is n equals d bits? But what is n? N is the number of bit I shifted in. Remember, it's like I started with 0 initially. Now, is it equals d bits minus 1? And remember, d bit is the number of data bits, whether it's 5, 6, or even if it's better, but maybe this is at 8, because I count from 0 to 8, which is 9. Anyway, you're asking basically, did I receive all data bits? And if the answer is no, you're going to actually go in here and add 1 to that n, because you just shifted 1 bit in, and you repeat the process. Once you shift all the data bits, parity bits, data bits, and everything, that n will equal the d bit minus 1. So if we are just talking about data bits in there, data bit will be, or d bit will be 8, minus 1 is 7, my n will be equal 7. That means I shifted 7 bits already. So I'm done receiving all the data bits. Basically, I'm saying, well, that my receiver in here, or my B register, actually has that value, whatever I wanted to shift basically. And okay, let me just, for the sake of argument, I just basically put these. So these are done. So what you need to do is you need to go and just make sure that you generate, or basically you will be in the stop bit. Okay, so you're gonna go to the stop bit. Of course, the S has to be zeroed. It was zeroed in here. Remember, it's like before you go in here, so the S got zeroed out. So you're gonna wait till the S equals SB, which is the stop bit tick. So these are two parameters we're gonna incorporate in our finite state machine. This tells the number of SB underscore tick is the stop bit ticks, basically whether it's, I'm waiting for 1, okay, that means this would be 16, 1.5 would be 1, like 16 plus maybe 8 or 7, and then another like 16 and 16, 32, if your stop bit is actually 2 bits. If it's not, you basically keep at it, and once you reach that middle of the stop bit, or actually finish the stop bit, you're gonna go in here, and here's an output that you will assert. This is the one of the few outputs that you have within your finite state machine. It's this one in here. This Rx will basically be asserted for 1 clock cycle, and then after you're done, you'll see that you will go back to the idle state in here. And that's how that receiver actually works. Of course, because whenever you're done, that value which we have put in here, let me just do that here. That value will be available in here, and it will be pushed out with the and will push to the FIFO afterwards. So now let me show you the Verilog code that actually describes this particular finite state machine. It's like any normal finite state machine. Well, first we have the inputs and outputs. They follow exactly what you see on the diagram. Of course, the clock and reset are not explicitly shown in here, but they're implied. It's a sequential circuit. I have inputs as these two in here, which is the RX and the S tick in here, and I have the outputs, which is this one here. Well, the RX done and the RXD out. That's what I called it. And of course, I parameterize the number of data bits, and I parameterize the number of stop bits in here, so that my code is pretty generic. And then like any finite state machine, I created local parameters for the states, and the states, I call them idle, data, start, and stop. Okay, and then I have the state register and the state next, like any state machine. And of course, in addition, because this is an FSMD, there's some sort of data that is moving around, I had to create some registers or registers to store the S, the N, and the B, and that's what you hear here. You have the S, okay, we have the N, and we have the B. Okay, then what happens next? Well, we have the state register, and actually all the registers in here. So the state register, like if you click on reset, I'm going to go to idle, and then the S and the N and the B, I'm just zeroing them out. Other than that, I'm just taking the next value. And how do I decide the next value? It's just a combinational circuit. It should be in here. And you can follow this here code on your own. It's really straightforward. It follows the diagram exactly. I'm just going to show you, for example, the start. Let's take a look at the start state, which is here. I'm just going to focus on the start state just to show you. So it tells me like, well, if you figure out that the state register is actually in start, you should do the following. First, you're going to ask, remember, these are conditional questions in here. Is s tick basically equals 1? It's the same thing. Like you can say like s tick equals 1 or just s tick. And if it's not, you basically, there's no else for this if, because you want to stay in the same state according to this one in here. And based on my default value, I'm just trying to declutter my code. This is why I didn't actually explicitly stated it, but what I did is I gave them some default values. So for the state next will be state register. That means if I don't specify, I'm going to stay in the same state. That's what happens in here. Now let's assume that if, well, it happens that s tick happened, so that is true. That means I have another question, and that's what you see in here. This is the other question in here. So in this question, I'm asking, is s tick register or sreg, remember, it's like I called it sreg and snext so that I can define whenever the next value is or whatever the current value is. Well, if it is the case that it is 7, I'm taking this. If it's false, I'm going to do this. Well, the false is the easy one, so this is where the else in here. So the false tells me all you have to do is just add 1 to that s. So what I did is I said the next value of s should be the current value plus 1. Remember, it's like I'm generating next and current. Anyway, if it was true, I'll do the following. I will make sure that the next value should be 0. This is what you see in here. And I'll make sure that the n next is 0 in here. And of course, I need to make sure that this line in here tells me that the next state, now the next state, remember, it's like because I didn't specify the next state in here, it will just take the default. But now in here, I'm actually moving to the data state. So I'm going to say, well, the state next should be data. And that's how the start actually state happens. The rest of them, here's the idle, here's the data, and here's the stop. I recommend that you pause the video a little bit and just make sure that everything actually falls through. And of course, in terms of output logic, if you take a look at it, usually output logics are specified, for example, like this one in here or this one in here. They're output logic, but well, for this finite state machine, I don't care about any of these outputs. They're internal. These S and the N and the B, they're internal, except for the B that I care about. Okay. And the reason why I care about the B, because it contains the value that I received. So what I'm going to say is the RxD out, which is this guy in here, is just going to be the same as B. That's what I'm showing you in here. Of course, what about the Rx done tick? Well, I embedded it in the code. You're going to see it in the stop state. So in the stop state somewhere, I have Rx done equals 1 in here. I could have just easily done it in here by saying, well, if my state is actually in the done state in here, or the stop state, sorry, and my s tick should be 1 and my s should be equals that, and if everything happens to be that, I can assert it. But what I did is I said, well, I'm asking these questions already in here. Let me just squeeze that in here. And of course, you're going to have to make sure that you give it a default value as well. And that's how we construct that receiver. It's just a finite state machine, and once you construct it, you don't have to worry about it. All you have to do is just plug it into your UART module, the main module.